Okay, we'll begin the class. All are able to hear my voice now?
Yes, ma'am.
Yes,
Okay,
ma'am.
so somebody
Yes,
should
ma'am.
tell me what did we discuss last class yesterday?
About corridor.
Wiring, ma'am.
Yes, about different types of wiring. What is house wiring? What are the different types of wiring?
How
Corridor wiring, then what else? One more type, staircase wiring, corridor wiring, we have discussed. Then depending upon the construction, we have discussed cleat wiring, wooden casing wiring, then conduit wiring. Then what is the definition of house wiring we discussed, and safety precautions we have discussed. Then what else?
Earthing.
Earthing.
Earning.
Earthing,
Earthing.
earthing.
So what is the necessity of earthing? What is earthing? What are the two types of earthing?
Pipe and plate.
Pipe and plate earthing we have discussed, and we have started off with the discussion of measuring instruments. All right. So I've shown you one slide. Okay. So this portion describes you how you can classify the different types of measuring instruments. So on what basis will you be able to do the classification? Tell me. Yesterday also I told you the same thing. So how will you be able to classify these measuring instruments? Based upon the quantity. Okay, based upon the quantity. Suppose if you want to measure volt means voltmeter. Ampere means ammeter. Energy means energy meter. Power means watt meter. So based upon the quantity that is to be measured, you are having one set of measuring instruments. Next comes how to classify instruments based upon the working principle. So on the basis of working principle, what are the various categories that you are having?
Moving coil and moving iron.
Moving coil, moving
moving
iron,
iron
dynamometer,
dynamometer.
induction type. Okay, so this is how you will be classifying instruments based upon the principle of operation. Next, last classification is how the quantity is being measured. Okay, on how the quantity is being indicated, you are having another set of classification, that is deflecting, integrating, and recording. So will you be able to give some example for recording instrument? It's easy thing to give some example, no, recording type. Could you give me an example for recording type of instrument?
Recorder.
Tape recorder, then instrument I
Microphone.
say. Instrument I say means, have you heard about CRO, cathode ray oscilloscope?
No,
No,
ma'am.
ma'am.
So do you know something about XY plotter or something?
No,
No, ma'am.
ma'am.
No, ma'am.
Otherwise, a simple thing. Suppose if you want to measure earthquake and all, they cite one name of the instrument, no, to measure the level of the earthquake. What is the name of that instrument?
I say.
Seismo.
Seis Seismometer, na?
Seismometer, ma'am.
So in recordings and all, they will show that there will be a pointer which will be moving, which will be making a distortion, na? Have you seen?
Yes. Yes, ma'am. In
Yes. So
movies.
that is what type of instrument? That is example for recording instrument. All right. In deflection instrument, you can easily tell so many examples like voltmeter, ammeter that you are using in common day labs. All of them are deflecting type of instruments. All right. So these are the three ways in which you can classify instruments. First, based upon the quantity that is to be measured. Next, based upon the principle of operation. Next, based upon how the quantity is being indicated. Okay. And the next thing that you have discussed about is the different types of torque that is necessary to produce the measurement. So what are the various torques that are necessary for producing the required measurement of any particular parameter?
Inertia,
This also we have
deflecting,
discussed yesterday.
control
First
torque.
one is deflecting. There will be a pointer or a needle mechanism which will be actually deflecting to show the value of the reading, but the needle cannot always deflect. Okay, it will be actually proportional to the quantity that you are going to measure. So you need to set it into an equilibrium position. So you need to develop an suitable opposing torque. That opposition torque is divided into two categories. One is inertia torque and the other one is control torque. So this inertia torque, I told you what is necessity for inertia torque. So what is inertia torque that you are having? What is the necessity? Why is it to be developed into the system? Inertia torque. The definition I have given you yesterday, isn't it? The pointer or the needle mechanism, initially it will be at rest position. So you need to initiate that from rest position. You need to actuate that from rest position. You need to make it move. Okay, so that torque is called as what torque?
Inertia torque.
Inertia torque. Alright, and in order to make the deflecting torque equal to the control torque, okay, then only that equilibrium position, balance position will be achieved. So in order to do that, you are having two types of control torque. One is spring control torque and the other one is gravity control torque. So if you see to this diagram, one diagram I am showing here. So this is your scale, alright, this is your pointer, needle pointer, and here you are having the spindle, and here you are having a spring. Okay, this is a spring actually. This is your spring, and here, so if the needle is made to move up, okay, because of the spring action, it will be pulled down. Alright, so that is called a spring control torque. Alright, next comes your gravity control torque. So if you see to this diagram, alright, this one, again you are having a scale, alright, and a pointer plus needle mechanism. Again you are having a spindle. To the spindle, a balance weight is connected. Okay, a balance weight is connected. And again, if the pointer is shifting over here, okay, with the help of this balance weight, it will be pulled down. Alright, so that type of control torque is called as what control torque? Gravity control torque. Okay, so control torque can be produced in two ways, either by using spring control torque and gravity control torque. Next comes your damping torque. So what is the necessity of damping torque? I have told you yesterday, no? What are the two types of damping torque that you can have in a system? What is the necessity of a damping torque? You know the answer or you do not know the answer? Tell if you do not know that I have forgotten. That is okay with me. What is damping torque actually? The pointer or the needle always moves on the scale, okay, but it should take just the right time to indicate the reading. Okay, that right time is set by the damping torque. Alright, so damping torque is classified into how many categories?
Air friction and eddy currents.
Air friction and eddy current damping. Okay, so air friction damping means you will be having a piston cylinder arrangement. This is your piston, sorry, cylinder. This is your piston, and this is your needle, and here you are having a spindle. So this spindle will be connecting both the needle as well as this arrangement of piston cylinder. So if the needle is moving, accordingly it will push the piston inside and in and out of the cylinder. So this is how you will be able to achieve air friction damping. Suppose if you want to achieve eddy current damping means there will be a small disc-like arrangement, vane-like arrangement, which will be made to deflect inside a vane, aluminium former. Alright, and this will work on the principle of eddy current development. So because of the production of the eddy current only, you will be able to restrict the movement of the pointer to just the right time it takes to indicate the reading. So this arrangement indicates your eddy current damping. So these are the two ways in which you will be able to produce damping torque. Damping torque, again I am telling you, it helps in the pointer to take just the right time to show the reading. Next, how to classify instruments. Only two types of instruments are included in your syllabus. One is MC instrument and MI instrument. I told you MC instrument is used to measure what quantity, DC or AC? Yesterday's class I told you, no, which type of instrument is preferably used for the measurement of what type of quantity? MC is used for DC or AC? Or shall I?
DC, DC.
MC is used for measuring DC. Alright. Suppose if you are making it to measure AC, it won't measure. All right, the current will reverse, the torque will reverse, and finally there will be no torque at all. So it will not be able to measure AC. So you won't use MC instruments for measuring AC, only it is preferably meant for measuring DC quantity alone. But if you see to MI instrument, preferably it is used for measuring AC quantity, but you can use it to measure DC also. Okay, that is okay. Now, how will you be able to classify MI instrument? Yesterday's class I taught you know what are the two categories that are coming under MI instrument. One is attraction type and the other one is repulsion.
Repulsion type.
Okay. So we are going to discuss these two types and MC instruments we are going to discuss. One of the types I have already taught you how it works, the attraction type. So this is your attraction type of instruments, MI. MI attraction type. Okay. So you are having this coil, okay, through which you will be circulating the current or the voltage which you want to measure. Alright, and this will be leading to the setting up of some magnetic field. So this is your magnetic field that is set up, that is shown by the flux lines here, in which you are going to keep a moving coil. Moving coil means a soft iron piece you will keep. So in this moving coil, you are going to keep the spindle which is connected to the pointer, and the pointer will be having a needle which will be pointing to the scale. Okay. So because of the field that is set up, this soft iron piece will adjust its position wherever the flux density is maximum. From the weak field to the strong field, it will move. So when the soft iron piece is moving, along with it, this needle will also move. So this is how the deflection is shown on the scale. So this type of instrument is called as what type of instrument?
Moving iron.
Moving iron, attraction type or repulsion type?
Attraction.
Attraction type. So next what will happen if it is to be a repulsion type, we need to discuss. So this diagram shows your repulsion type of moving iron instruments. Here also you will be having two coils. WC represents your working coil. Okay, and MC represents your moving coil. Alright. So you are having two iron pieces here. As you can see, they have pointed out the name of this iron piece. This is one iron piece and this is one iron piece. Two iron pieces will be there. So one is always connected to the stationary part. Alright. The name of that iron piece is called as what? One of the iron piece will not move. Okay, it will remain stationary. The name of that iron piece is called as what?
Fixed iron.
Fixed iron. Okay, another one will be movable. Okay, this one will be a movable iron piece. Alright, movable iron piece. So when again you are going to pass the current or the voltage which you want to measure through this working coil. So it will set up the magnetic field. But what will happen is both these iron pieces will be magnetized with the same polarity. So if they are magnetized with the same polarity, what will happen? What will happen? Again I am telling you, through this working coil, you are going to pass the voltage or the current which you want to measure. Okay. So it will be setting up the magnetic field. Alright. In that magnetic field, you are keeping two iron pieces. One is remaining fixed, stationary, that is fixed iron piece. Other one will be set into motion. But these two iron pieces will be polarized with the same polarity, either north pole or south pole. Both will be polarized in the same manner. Alright. So what will happen as a result? That is my question. Both will be north-north or both will be south-south. So you know what will happen. Like poles will be
Repulsion.
Repel.
Okay. But one is fixed. Which one will move?
Moving.
This is a fixed. Okay, so it will not move. Alright. So this is the movable iron piece that it will move. It will get repelled from the standard position. So if this is moving, this is connected to what arrangement here? This is the movable iron piece which is getting repelled. So that is connected to what arrangement now? This is your pointer with the needle arrangement. So this will also move or it will not move.
Move.
It will
Move. It will
move.
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 So with this movement, it will move on the scale. So thereby the reading will be indicated. So this is how what type of instrument works. What type of instrument is this?
MI repulsion.
MI repulsion. Okay, again tell me how will it operate MI repulsion instrument? There will be two coils. One is working coil, one is moving coil. The moving coil arrangement will be having two iron pieces. One will be fixed iron piece that is not moving. Another iron piece will be set into motion. So what you are going to do is through this working coil you are going to pass off the current or the voltage which you want to measure. So it will set up the magnetic field in which these two iron pieces are placed. So they will be polarized to either north polarity or south polarity, same polarity. So because of which one of the movable iron pieces will deflect in its position, it will get repelled. That iron piece is actually connected to the pointer and needle arrangement which is moving on a scale. So this will also get shifted in its position, thereby it will indicate the reading. Okay, whichever value you want to measure, either voltage or current. And here you can see for yourself which is giving you the control torque. What is present here? BW means a balance weight. So what type of torque is giving you control mechanism? Is there any spring present here?
No, no.
No.
No spring. So what type of control mechanism happens here?
It, gravity.
Gravity.
Gravity. Okay. So this is moving iron, attraction, repulsion. Both are capable of measuring AC as well as DC. But preferably they are meant for measuring AC. Okay. Next you need to know how the MC instruments work. So we'll discuss that. So you can see this diagram. Alright. So this is your permanent magnet MC instrument, that is permanent magnet moving coil instruments. So why is it called as a permanent magnet is because you are seeing here a south and north pole. These are nothing but permanent magnet pieces which will be setting up the necessary magnetic field. So in between the permanent magnet, you are keeping the coil, moving coil actually, or movable iron you can say. Okay, so this moving coil, it will be subjected to the magnetic field. Okay, and it will be carrying the current or the voltage that you want to measure. So what will happen as a result? This is similar to a generating effect or a motoring effect. Again, I'm telling you, this is your good example for permanent magnet moving coil instrument. The south and the north pole represent your permanent magnet pieces, which will be setting the magnetic field. In the magnetic field, you are going to keep a moving coil. And to this moving coil, you will be passing current or voltage which you want to measure. So this arrangement is similar to motoring effect or generating effect. You know what is the working principle of generator and a motor? I've told this 3 or 4 times in different times, both in lab as well as theory. So how do they differ? Principle?
Motor.
What?
Motoring.
So generator means you are going to keep a conductor rotating in the magnetic field which will be generating dynamically induced EMF. But if it is to be a motor means what will happen? You are passing current through the conductor which is not initially rotating. Same effect is seen here or not?
Yes, ma'am.
Yes, ma'am.
Yes. So what will happen? That is the question. How it is set into rotation actually? What will be produced? Initially, this moving coil is not at all rotating. Okay, it is being passed through the current or the voltage which you want to measure. And you are having a magnetic field present here, which is stationary. So what will happen as a result? I told you this What will be generated? A twisting force will be generated. I told you, no, twisting force is equal to what? Torque. So that torque will set this moving coil into rotation. So it will start to rotate. Okay. So with it, what will rotate? If this is starting to rotate, it is attached to the pointer and needle arrangement. So this will also deflect and move on the calibrated scale. So this is how the PMMC instrument works. Okay, permanent magnet moving coil instrument. It works in this way only. It is preferably meant for measuring DC quantities only. It cannot be used for measuring AC. If you are using it to measure AC, the current will reverse, the torque will reverse, and this will become problematic, and finally torque will be nil. And no deflection will be possible, and no reading will be indicated. So it is preferably meant for measuring DC quantities only. Alright. So the name of the instrument is what instrument?
MC.
MC, permanent magnet moving coil instrument. So you are going to keep north and south pole, which will be setting up the magnetic field in which you are keeping a moving coil, which is being passed with the voltage and current which you want to measure. So as a resultant of which a force will be generated, that is twisting in nature, which will be setting this into rotation. With it, the pointer and needle will also rotate on the calibrated scale, indicating the reading. Okay. And what type of control torque is produced here? Same arrangement, same diagrammatic representation only, but they are given different ways. So what type of control is produced here, which will oppose the deflecting torque?
Spring.
Spring.
Spring
So
control.
spring control torque. Alright. So that's all. Alright. With this, that unit number 2 is over. Next unit is all about devices, electronic devices. So that we'll see now. So what are the various devices you know that you have studied in your physics class? Just name the devices now. Devices,
Meter.
different devices. Huh?
Box office box.
Box office box. Devices, that is
Post
electronic
office box.
devices, semiconductor devices.
Post office
What?
box. Post office box.
Who is giving me this answer? I will give you 2 scoldings, super, if you are telling post office box. Are you an idiot to give an answer in a class like this? Why post office box is related in what manner with the electrical and electronic subject, you tell? So I am talking about semiconductor electronic devices, physics, in relation with physics. I am telling and you are telling post office box.
Okay, ma'am. Sorry, ma'am.
So what are the various devices that you have studied in your physics class, lower class? You have conducted experiment also in lab with these devices. So name some of the semiconductor devices, electronic devices.
PN junction diode.
Semiconductor devices, PN junction diode, then PN diode, then what else?
Solar cell.
Solar.
LED.
Rectifier application, LED, then Zener diode. Okay, and then transistors. Okay, under transistors you are having different categories, one of which you worked in your lab. The name is BJT, that is bipolar junction transistor. Then you are having so many other transistors also, that is MOSFETs. Okay, all these PN junction, everything you will discuss in this unit. Unit number 3 is all about electronic devices only. So again, tell me what are the various semiconductor devices. List some.
Photocell.
Photocell. Okay, then you have to start from the very basic device. So basic devices, PN junction diode only, then Zener diode. Many variations of diode is possible. Schottky diode, Varactor diode. So many different possibilities are there. If you come to transistors, means again you are having different variations. So name some transistor devices.
BJT.
BJT is expanded as bipolar junction transistor. MOSFET means metal oxide semiconductor field effect transistor. IGBTs are there, insulated gate bipolar transistor. So IGBTs are not included in syllabus. Still so many other devices are there. But for you in syllabus, PN junction diode, Zener diode, transistors are included. So we will study about the construction, operation and characteristics of these devices. Okay. That will be finishing of unit number 3. So first let us begin with the PN junction diode. So this is the symbolic representation for what diode?
PN junction
Zener.
diode.
PN
PN
junction.
Zener diode. PN
PN.
junction diode. So this is a very basic semiconductor device. Okay. From this only all the other devices were developed. So this is called as PN junction diode. And what are the two terminals of the diode?
Positive and
What are the
K.
two terminals of the diode? You are having two terminals marked as A and K. What is A and K?
A must be positive and K must be negative.
A is anode, K is cathode. Okay, don't say positive, negative. That is wrong way of interpretation. So A means what?
Anode.
Anode. K means cathode. So these are the two terminals of the PN junction diode. So PN junction diode is a how many terminal device?
Two terminal
Two
device.
Two
terminal.
terminals. Okay, so if this is a symbolic representation, you have to draw the symbol of diode like this only. It's a two terminal device. Okay, next. How you will be able to create the PN junction diode? That is the next question. I think in your physics class you must have studied what is p-type material and what is n-type material. So if you are going to physically keep in contact half p and half n, thereby forming a PN junction, that diode will be called as a PN diode. Understood how the construction will happen? You have to take half doped a semiconductor material which is half doped with P and half doped with N. You connect it or you put it in physical contact. This will be creating what type of diode?
PN junction diode.
PN junction diode. So you have to take a semiconductor diode, you dope it. Doping means addition of impurity. Okay, doping means addition of impurity. So to the semiconductor diode, you add doping by half by P material and half by N material. If you put it in physical contact, it will be creating a junction that is called as PN junction, and the diode will be called as a PN diode. Next, construction and electrical equivalent is over. Next thing, application. So where will you see this PN junction diode being used commonly?
LED.
General knowledge. LED. LED is quite a different type of diode. Okay, it is not an application. So next, what are the various applications for filtering,
Electronics
for
devices.
filtering and clipping, clamping? Okay, for all wave shaping purposes, for switching applications, you will be using a PN junction diode. So you can use this PN junction diode in electronic applications, opto applications, industrial applications and instrumentation applications. So this is regarding the application. Next we'll move on to the characteristics. Okay, so the characteristics is drawn between V and I actually. So V and I, between these two parameters, if you are drawing a graphical representation, it will be called as a VI characteristics. So this VI characteristics are divided into two. The characteristics that you are obtaining under forward bias condition and the characteristics that you are obtaining under reverse bias condition. So you have to combine these both, and then it will be a total VI characteristics of the given PN junction diode. So we will discuss this. So I told you biasing. What is biasing? What do you mean by biasing? Biasing. Generally, what is meant by biasing?
Forward or reverse.
So you can see here, this is your semiconductor diode which is half doped with P and half doped with N. So this is how constructionally a PN junction diode will look like. And you are applying what here? What is being applied here?
Voltage.
Voltage.
Yeah.
DC voltage or AC voltage is supplied?
DC.
DC or AC is supplied. What are the two
DC.
terminal markings? Plus and minus are the markings. So what type of supply is this?
DC.
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 DC. So this will be called as the battery or biasing. Okay, DC bias. This will be called as DC bias. Okay, so you understood what is the meaning of biasing now? What is biasing?
The battery source, voltage source which we applied is the
Yes,
battery.
we are going to excite it by using an external source. Okay, that is called as DC source in especially that is called as DC biasing. So you are going to connect one source, voltage source, that will be called as a bias. Alright, and that biasing will be split into two. One is forward bias and the other one is reverse bias. Okay, RB means reverse bias and FB means forward bias. Forward bias and reverse bias. Okay, so forward bias means between plus V and plus I you are going to draw the curve. Reverse bias means between minus V and minus I you are going to draw the curve. How that curve nature varies you are going to discuss with the help of this diagram. Now that DC bias is indicated by W. Okay, and this PN junction, it will be creating its own internal barrier, that is the junction barrier, that is indicated by V. Okay, internal barrier voltage is indicated by V, the applied bias is W. Okay, so under forward bias, I will tell you what is forward bias. I think I have already told this in lab class also. So what is this terminal marking? This terminal marking is given what symbol?
Positive.
Positive. So here other side you are having
Negative.
negative. So here you are having positive, here you are having negative, and positive is connected to what terminal and negative is connected to what terminal?
Positive is connected to the P and the negative is connected to the N.
So if you are giving such biasing, that will be called as what biasing condition?
Forward biasing.
Forward bias. So plus is connected to P type and minus is connected to N type, then only it will be called as forward bias. Okay, remember this, you should not forget this thing. I think you must have studied this in physics class anyway. You are sitting as it is new to you. So anyways, I am telling it again. You are going to connect positive terminal of the supply to P type, negative terminal of the supply to N type. That type of biasing condition is called as forward bias, that you should never forget. Okay. Now, if you do so, I am telling you this is a semiconductor diode, half doped with P and half doped with N. Now, before discussing that, I would like to give some small intro. Okay, there are two types of semiconductors actually. One is intrinsic, other one is extrinsic. Okay, so what is the meaning of both? Why am I calling intrinsic and what is the meaning of? Or otherwise, tell me what word I have indicated here.
Pure.
Intrinsic, pure.
Type
Pure.
So
semiconductor.
a very pure semiconductor without any impurities being added to it, that type of semiconductors will be called as what type of semiconductor?
Intrinsic.
Intrinsic. But if you are having a pure semiconductor, it will be having a problem. Okay, that problem is it will not be superconducting at room temperature. Very low conduction will be observed at room temperature. So you want to improve the conduction. You know what is conduction? What is conduction actually? If you say any circuit is there, it is conducting, I am telling. So conducting means flow of current. Okay. That current only will be given to the load. So if you are having a very pure semiconductor without any impurities being added to it, the problem is it will not be able to conduct at a higher level at room temperature. So you want to increase the conductivity. So what you are trying to do is you are going to make it impure. So you are going to add up some extra impurities to the pure semiconductor, making it to be what type of category?
Impure.
Impure.
Extrinsic.
What is the name? Extrinsic.
Extrinsic.
Okay. That process of adding of impurity is called as what?
Doping.
Doping. Okay. And what type of impurities can be added? Either pentavalent or trivalent impurities can be added. If pentavalent, if you see what are the examples, these questions may be asked in MCQ, so make a note. What are the examples for pentavalent impurity? Pentavalent impurity I have given, no. What are the examples for pentavalent impurity?
Arsenic,
Arsenic, antimony.
Arsenic and antimony. If
antimony,
you go for trivalent impurity means what are the examples? Aluminium and
Aluminium, boron.
boron. Okay, so you are going to add these impurities either pentavalent or trivalent and make it to be an extrinsic one. Okay, that is how you will be getting p-type material and n-type material. And one more thing you have to remember, there are majority charge carriers and minority charge carriers for each every type. So if you consider p-type, the majority charge carriers will be holes. Okay, holes. Majority charge carriers for p-type will be holes. When it comes to n-type, n-type majority charge carriers will be electrons. Okay, you have to remember this also. So for p-type, what are the majority charge carriers?
holes,
Holes.
Holes. For n-type, what are the majority charge carriers?
Electrons.
Electrons. The minority charge carriers for p,
Electrons.
electrons are minor, and here holes are minor.
Major.
Okay, that
Okay.
you remember. All right. So with that only you can understand the biasing property and all. Now moving on to plus connection. Plus is connected to P where the majority charge carriers are what?
Holes.
holes,
Holes. See, holes are actually positive. Okay. Electrons are actually negative. So what will happen as a result? Here the majority charge carriers are holes which are positive in nature. All are positive. Here also positive polarity is there. So what will happen? Positive, positive. What will happen?
repel,
Ripple.
Repel. Okay. So because of this particular condition, the majority charge carriers will get repelled and it will start to go towards the junction. Okay, this is your junction. It will try to get repelled towards the junction. Now here you are having negative polarity. The majority charge carriers of N is electrons, which is again negative. So what will happen here? Negative polarity here, electrons are negative here, which are majority charge carriers. What will happen? Negative, negative. Again, what will happen?
Repel. Repel.
Repel.
repulsion,
So electrons will also try to move towards the junction. Okay, so here hole flow and here electron flow, both will move towards the junction, and inside the hole the electrons will try to combine. Okay, all right, and it will also result in free flow of electrons. Okay, it will result in free flow of electrons. Free flow of electrons. So this will be resulting in current flow also. All right. So this is how conduction happens or the device does not conduct. Under forward bias now, conduction happens or no conduction at all. I am telling there is a free mobility of electron hole pair. Okay. So which will be resulting in current flow. Current flow means equivalent to what phenomena?
flow of electrons,
Conduction. Okay. So
conduction,
conduction. So in this forward bias, the device is conducting or not conducting?
Conducting.
Conducting. Okay, this device will be conducting only under forward bias condition. That you remember. Have you understood now how the operation happens under forward bias condition and what is forward biasing?
yes,
Yes, ma'am.
ma'am,
Tell me again what is forward biasing. How should you give connection?
positive with
Positive charge to
P
the
and
P
negative with the
and negative to the N.
So what will happen as a result if you are giving such a biasing?
forward biasing will happen.
What will happen as a result inside this diode construction? This is positive and here holes are positive, so because of which hole flow will happen, it will get repelled to the junction. Here it is negative, electrons are getting negative, so electrons are also repelling and it will be getting moved towards the junction. So free flow of electrons will happen, because of which current flow will be there and conduction will happen. Okay. Now, we will discuss this in detail with the help of the characteristic curve. Now, we are drawing a curve between Vf and If, that is under forward condition or reverse condition. F indicates what?
Forward.
Forward.
Forward. Okay. And now I am telling you this is my cut-in value, okay, which is indicated by V naught. So as long as Vf is less than V naught, that is your cut-in value, what happens? What happens? My forward voltage is very less when compared to the cut-in value. So if this is the case, is there any, this is the part actually. So is there any current flow?
No.
No. Okay, so here If is equal to 0. First case, when the forward voltage, when it is less than the cut-in value, there will be no current flow. Alright. Suppose if it is a germanium diode, then this 0.3 is your cut-in value. So when Vf is becoming equal to that cut-in value, that is 0.3, now what happens to the current?
Current will start to flow.
Yes, this diode starts to conduct. But for silicon, what is the cut-in value? That is for germanium diode. What about the cut-in value for silicon? That is 0.7,
0.7.
not
0.7.
0.7. So this is a cut-in value. When Vf is becoming equal to 0.7, that time it will start to conduct. Okay. This is because two cases. I told you there are two voltage. This is your W, that is your applied voltage, and this is your internal barrier voltage. This is your internal barrier voltage. Generally under forward bias, both will be opposing. Okay, W and V will be both in opposition. So as long as Vf is less than the cut-in value, okay, cut-in value, what will happen is this internal barrier will not allow the free flow of electrons. Okay, this internal barrier will be strong and will not allow it, prevent the flow of free mobility of the charge carriers. But now second case, that cut-in value is reached. Okay, that cut-in value is reached. Now what will happen is this W will be in pure opposition with this voltage and it will overcome. Alright, it will overcome the internal barrier. So now the barrier will be easily broken and the junction will be reduced, which will be resulting in free flow of carrier electron hole, which is resulting in conduction. Okay, understood the forward bias
Ma'am.
operation? Yes or no?
Yes, ma'am.
Okay. So that internal barrier region will be also called as depletion region. Okay, the depletion region. Okay. Next, let us see what will happen if you are giving a reverse bias condition. Now you are connecting plus 2p and minus 2n. Just I am going to reverse this. Instead of plus minus, I am going to give negative here and here I am going to give positive. Okay. Now which is connected to which here in this case?
Negative to
Negative
P
is
and
connected
positive
to
to
the
N.
P.
Negative connected
Positive
to
is
P and positive connected to N. So this type of biasing
N.
is called as what biasing?
Reverse.
Reverse biasing. Okay, understood what is the difference between forward bias and reverse bias?
Yes, ma'am.
Okay, so now let us discuss what will happen under that condition. So you can see here for yourselves. So here this negative terminal is connected to P and positive is connected to N. So it will be reverse bias condition. And again this is your internal barrier and this is your applied voltage. Okay, and this is your reverse bias characteristics that is drawn between reverse current and reverse voltage. Now how that characteristics is obtained we are going to discuss again. Okay, now because of this connection that you are giving like this, here negative, you already know what are the majority charge carriers in P. So what are the majority charge carriers in P?
Holes.
Poles.
Poles, which are of what polarity?
Positive. Positive.
Positive. So here positive, here it is negative. So what will happen?
Attraction.
Attraction. The holes will try to move towards the negative polarity. Okay. Now, if you see to the other side here it is positive. You know what are the majority charge carriers in N type? So what are the majority
Electrons.
charge carriers?
Electrons.
Electrons, which are of what polarity?
Negative.
Negative. So here negative, here positive. Again, what will happen?
Attraction.
Attraction. So the electrons will try to come towards the positive terminal. So in between, you are having the junction that is called as a depletion layer. So what will happen here is all the electron and holes will try to come to the other side. So the layer will be depleted of mobile charge carriers. Okay. So this layer will become depleted of mobile charge carriers. So if mobility of the charge carriers is stopped, then what will happen? The junction will also become big. So what will happen? The mobility, free mobility of the charge carriers is not happening. So the current flow will also be not there. So in this case, the device is in conduction or no conduction?
No conduction.
No
No
conduction.
conduction.
No
Okay.
conduction.
Okay, no conduction. Only if the free flow is there in this direction, in the junction, then only the current flow will be there and the device will be conducting. But all the charge carriers are getting moved in the opposing direction. If the junction is getting depleted of free mobility of the charge carriers, which are actually the reason for the current flow. So because of this particular reason, ideally the current flow will be nil. Okay, but practically some small, very minute amount of current will flow, which is of what value? Mu means what?
Microampere.
Microampere. Microampere is very minimal, okay, 10 to the power minus 6, right? So even though ideally, literally you can say that there is no current flow, still some minimal amount of current, very minimal amount of current will flow, which is reverse saturation current. Which is called as what current? That
Reverse
minimal
saturation.
amount of current is called as reverse saturation current. I am telling there is no free mobility of charge carriers, but still you are having light heat phenomena. Okay, light is there, heat is there, so thermal energy is present. Yes or no? Thermal energy is not there or there? Heat and light are corresponding to thermal energy or not thermal energy?
Yes, ma'am.
Thermal. Okay, so even though the action is not happening, conduction is not happening, still there is light, still there is heat. So because of this light and heat that is hitting on this device, there will be some thermally generated carriers. Okay, thermally generated holes, thermally generated electrons will be there. Those are the reason for this reverse saturation current. Okay, this thermally generated holes and electrons, they will travel through this junction. Okay, this thermal generated carriers, both the holes as well as electrons will travel through this junction and they will hit the covalent bonds. Okay, they will hit the covalent bonds, so they will break it open. So when the covalent bonds are broken open, then still more and more electron hole pairs will be generated, and this will happen in a cumulative effect. Okay, again the free released electron holes will go hit another covalent bond, it will release some more electron holes. This action will happen like a chain reaction, cumulative effect, addition and addition and addition. So finally what will happen is some breakdown. Okay, all right, that breakdown is called as avalanche breakdown. Okay, when that breakdown happens, the reverse saturation current will become very large and the device will not be able to cope up. It will get damaged because the power dissipation in this junction will become very high. So the device will get damaged. Okay, all right. So you cannot operate this PN junction diode in reverse bias. If you are trying to operate means at breakdown it will get damaged because it will not be able to cope up with the power dissipation that happens at a higher level in the junction. So it will get damaged. But you want a diode to operate at the reverse bias condition also without getting damaged. For that, what you can do is you can increase the doping of this diode. Okay, you know what is doping? What is doping?
Adding of impurities.
So you add higher level of impurity to the diode. Then that diode will be turned into another diode that is called as what diode?
Xeno
Xeno
diode.
Xena diode.
diode.
A Zener diode. And why you are doing that? Why you are converting the original diode into a Zener diode? Because originally as such PN junction diode, is it capable of withstanding the breakdown at the reverse bias or it's not capable?
Not
Not
capable.
capable.
Not capable. Okay, because what is avalanche breakdown again? Very important question. Avalanche breakdown. During reverse bias, I already told you that this PN junction diode, it will not be conducting. Ideally, there will be no current flow, but still there is light, still there is heat. So thermal generation of electrons and holes will happen. Okay, and these thermally generated electron hole, they will go hit the covalent bond. Alright, and this covalent bond, when they are being hit, they will release extra holes and electrons. Again, they will go hit other covalent bonds. So this action will happen in a chain, which will be resulting in what is the name of the breakdown?
Avalanche breakdown.
Avalanche breakdown. You know what is avalanche, isn't it? It will usually happen in snowy, hilly area. Okay, like that. The chain reaction will lead to the breakdown of this device. That is called as breakdown voltage. And when this breakdown happens in this junction, the power dissipation will go very high, which the device will not be able to cope up with. So in order to make the device cope up with this reverse breakdown, you are adding extra impurities to the device, making it to be what type of diode?
Zener diode.
Zener diode. Okay. Now, what is the symbolic representation that you are having for a Zener diode? Again, what
That
are the two terminals that you are having?
anode and cathode.
Anode and cathode. Same terminal, but if you are referring to the symbol will be having an EZ. Okay, this is an EZ shape. So this is how you will be able to differentiate a Zener diode and a PN diode. PN diode will be having one single line, but if it is to be a Zener diode means you have to indicate an EZ shape. So how you are able to differentiate Zener diode and PN junction diode? PN junction diode will be lightly doped. Zener diode will be heavily doped or lightly doped?
Heavily.
Heavily. Okay. And if you discuss about the forward characteristics are same or is it different?
Same.
Forward
Same
is
only. Forward bias condition will be same both for PN and Zener diode. Only the reverse bias conditions will be differing. Okay. So in this reverse bias, what will happen is here a different breakdown will happen that is called as a Zener breakdown. Not avalanche breakdown. Here a special breakdown will be happening. The name of the breakdown is what breakdown?
Zener breakdown.
Zener breakdown. Okay. How these two are different, I will tell you. I have already told you that if you are working a PN junction diode under reverse bias, it will not be able to cope up with the power dissipation at the junction and the reverse bias condition, so the device may get damaged. So in order to make it cope, you are adding extra amount of impurities to the device, making it a heavily doped one. If you are doing this heavy doping, the breakdown will occur here very early. Okay, not at a very large reverse saturation current. Here it will be, the breakdown will be very early. Okay, breakdown happens very early. Alright, very early. So because of the doping that you are giving very high, the breakdown will happen very early. And if you can see to the characteristic curve, this is IR. Alright. So saturation current as it increases, what is happening to the voltage? Voltage is remaining constant or not constant? IR is increasing. What about the voltage?
Voltage
Constant.
decreasing.
Voltage remains constant. Okay, that is happening at Zener breakdown. Okay, V is that represents Zener breakdown voltage, and because of this particular reason, only Zener diode is specially meant for what application? Voltage regulator. Okay, voltage regulation is possible under what biasing condition? Reverse bias or forward bias?
Reverse bias.
reverse bias. Okay. How the breakdown occurs, we'll discuss. With that, we'll discuss class. Okay. So I already told you that you are going to heavily dope. Okay, heavily dope. Okay, which will be creating a strong nature of electric field. Here you do not need light and heat to rupture the covalent bond. Because of the heavy doping that you are giving, the electric field in the junction will become very high. Direct rupturing will happen. Okay, because of the strong electric field, the covalent bonds will be directly ruptured, which will be releasing electron hole pairs. Again they will go hit the covalent bond, which will be releasing more and more, and this type of breakdown is called as what breakdown?
Zener breakdown.
Zener breakdown. Avalanche breakdown means covalent bonds will be ruptured by thermal process, that is by heat and light. But in Zener breakdown, the rupturing of the covalent bond will be directly happening because of the heavy doping, because of the high electric field, that is about 6 volt. You will be having a direct rupture of covalent bond. That is how these two types are differing, and here depletion layer will be very thin. Okay. So with this we will close class. Alright, we have discussed what two type of devices today.
PN junction diode and Zener diode.
We have discussed the construction, symbolic representation, and the characteristics, and the two biasing conditions. So what are the two biasing conditions that you are having?
Forward and
Forward
reverse.
bias.
Forward and reverse
Back.
bias.
Reverse.
So all of you understood, huh?
Yes, ma'am.
Yes, ma'am.
Okay, with this we all can disperse, ma. Okay, I'm having some work. Okay, so
Ma'am,
I want to close class.
Okay, ma'am.
ma'am, you had
What?